seminars. We have a special guest today from mechanical engineering here at Berkeley. Dr. Hannah Stuart is a associate professor in again in ME. And she received her PhD at some school across the Bay. I don't recognize the name. Her research focuses on understanding the mechanics of physical interaction, and she'll be talking a lot about that and how they apply to different types of robotic systems and quite a variety of systems. And you know, some of the things that she'll talk about specifically are sort of research into dexterous manipulation and looking at the challenges and solutions for those type of problems. So, and I guess her applications, again, as I say, are pretty broad. They range from remote robotics to assistive orthotics. I guess I pronounced that correctly. She's received many awards, but without further ado, I'll let her go ahead and get started, and thank you for coming.
Can you hear me? Is it going through the microphone? Yeah? Okay, good. Thank you so much for the introduction. It's really a great pleasure to be here today. I already see a couple familiar faces. Yeah, so what I'm going to do is introduce a couple technologies that our lab has been working on more recently, after giving a brief introduction of my own training past. And I will stop after each of the two primary technologies and see if there's any questions emerging, and I'd love to hear what you have to ask and say. So today I'm really focusing on adding a sense of touch. So this is sometimes called tactile sensing in robotic realms, but obviously humans also have a sense of touch. We actually have a very rich sense of touch, and we also have squishy fingertips. And so there is this space of how do you create a sense of touch in soft systems that's very challenging to do mechanically, but extremely important. And so we're going to talk a little bit about sense of touch and how we can add it. So just to give you a brief background, I actually got my start working on this humanoid robot. It's called Ocean One. This was back in 2016 or 17. So I was a PhD student at Stanford, the other school. And this is a mission that we did where we actually went to the Mediterranean. It was so amazing and so fun to be a student on it. My job was to build the hands. So the part in white, the fingers, and the section that sort of looks like the palm, I built that with my own hands. So a lot of it's 3D printed in sort of maker spaces, so cast rubbers. And really the innovation of this design was around the fact that it has only one actuator, yet can perform all these different sorts of grasps, which are essential for undersea operation. And ultimately it was able to grasp an artifact from a shipwreck and actually retrieve it and bring it back. So that was super, super exciting. Well, one of the really scary things as a student was the director of the project, Osama Khatib. At one point, he was like, you know, if the hands break, all we can do is swim around and look at stuff. Like we can't do physical tasks, right? The hand is where the rubber meets the road, and it needs to be reliable and it needs to work really well. And that's really why I ultimately focused my thesis on how you could do as much as you could with only one actuator, because it limits the seals, it makes it very physically robust, and it has some degree of compliance in it. Yes. Yeah.
Well, I was curious about robots, and why did you make it so humanoid?
Well, that's a great question for Osama. So Osama Khatib, the director of the project, had this vision to make it a humanoid shape. Really, I think there's this underlying hypothesis, which I think still needs some study, but the fact that you have two arms that are approximately the size of a person and a body that's approximately the size of the person, the idea is that it's easier to teleoperate. And then there could be human-like expression through body motion, such that you actually have this telepresence, so you can interact both with the environment and with other divers in a very naturalistic way.
That makes sense for communication.
Yeah, so that's definitely yeah, and it's an ongoing project. I don't work on it anymore, so I know that it's changed and everything, but
things I see robots.
Yeah.
Why do you know? Yeah.
Yeah, so you usually see humanoids in environments built for people. So we built all of our door handles and everything for a humanoid form. So therefore, we've kind of optimized the environment for ourselves. And so there might be advantages, functional advantages to being humanoid. Yeah, and then there is that sort of societal and human-robot interaction aspect. And there is a push for humanoids today, and I think, you know, that's one of the reasons. Okay, so that was the project that I was on, but my advisor, my academic advisor was Professor Mark Kokoski in mechanical engineering. And so he was a major influence on my perspective. And this is one of my favorite quotes from him. Like the performance of a sports car, which is ultimately limited by the tires on its wheels, the performance of a robotic hand is limited by the skin on its fingers. You could have the most kinematically complex and beautiful humanoid robot with articulated fingers. And then if it has slippery contacts, it's going to have a lot of trouble doing stuff. It's going to be dropping objects all over the place. Similarly, you could have a very beautiful sports car, and if you put the wrong wheels on it, it's going to go slipping and sliding all over the place, right? So even though it's just rubber, you really can't forget about the mechanics of the contact where the rubber meets the road. And so I focused a lot of my career, both at the end of my thesis as well as in my faculty position, on that question, the rubber. So underwater, this was something we could play with in terms of adding suction flow or flow going in and out of the fingertips, kind of like you're pulling in or pushing it out. You know, fish use suction feeding. Maybe an underwater humanoid should have suction-y fingertips. So on the left-hand side, we're actually ejecting water to create a lubricating film so that it actually purposefully slides along the finger to create a grasp. And then on the right-hand side, you can't really see it, but we are pulling flow through. And what you can do is use a pressure transducer. So who remembers that when you have a pipe and flow going through it, the pressure that the pipe experiences is going to change with flow rate. Okay, so this is like fluids 101. That's what we're using. So the fluid is going through this pipe. On the right-hand side, it's in white. And then high up, we're measuring that pressure, wall pressure, which tells us the rate of flow. So we can actually also do touch sensing underwater. Okay. So that's the end of my underwater spiel. I haven't done as much of it in my thesis, and I'm really excited about applications in air because a lot more people work on that. And so one of the first things I'm gonna start thinking about is, could we use flow in air in a meaningful way, not just underwater? So when I'm thinking about robotic systems in an air environment, a really common one is in this sort of scaled up automation. Okay, so you're going to have robotic systems, conveyor systems, you know, trucks to move things around. But it's important to point out that there are still a lot of people in this environment as well. This is an optimized system. So what is the role that the person has in this system that's so critical that they do it and not a robot today? So if we look at the robotic systems that are intended for these kinds of environments, on the left-hand side, you can see Boston Dynamics has this beautiful sort of sucker array. It can grab regular boxes, okay? And then on the right-hand side, we have a kind of scooter robot that can scoot around these different shelving units. So a lot of this has to do with sort of more global mobility, whether it's, you know, a couple feet or a long distance. We're generally moving regular boxes around. Robots are amazing at that, okay? Well, where I see the person really excelling and way outperforming the robot is going to be in more fine-tuned manipulation, something that has to be more adaptable. So in this case, we have these large sort of shelving units. The person needs to open the tape, put their hand in, make sure they're grasping the right object, pull it out, and then move it into a box. That's actually a really complicated manipulation, and there's going to be lots of contact and sliding between the hand as well as the object and other objects. And people are just way better at this currently today. And I believe really strongly that one of the major advantages that we have is a sense of touch, okay? Which most robots don't usually have, especially at the dexterity and level that humans do. So just for a really quick experiment, to get a sense of your own sense of touch, what I want you to do is put your hand like just flat on your lap or somewhere in front of you and just hold it there. What do you feel? You feel temperature, maybe you feel overall shape like the curve of a thigh. Now, if you slide your hands, you're going to feel all the dust on your laptop. You're going to feel the texture. You're going to feel whether you're wearing jeans or something else, right? So those are actually two different kinds of tactile sensors. One is distributed pressure. The other one is really high frequencies, kilohertz frequencies, signals at very low amplitude, and they give you different information. And then when you couple that a suite of sensors with different behaviors, you get new information. And that is actually the generic definition of haptics, the coupling of touch and behavior or motion to get more information. Okay. And so really and then we've lived for me, 36 years in this body with this sense of touch. I've generated really good models for what denim feels like versus cotton, right? So I can really understand the situation. Robots are not even close. And there are tactile sensing technologies emerging, but they're not matching the abilities that we've seen in people. Okay, so I want to talk a little bit more about sort of the state of the art in how people are starting to apply touch sensors, especially in soft systems. So I didn't say this before quite explicitly enough, but the Ocean One hand has compliance. And that's because in its dives, it would drag its hands along the ground, but then it needed to grasp a very fragile artifact. So actually having compliant elements is a real strength in hand design. And so how are people applying sense of touch to soft hands? Well, here's a work that I'm a fan of out of Antonio Beakey's group, where they're actually just using binary signals, no fancy pressure sensing or anything like that. They're coming down. When they first make contact, they then start to rotate about that contact until they make two contacts. And then they rotate about that line to then make a full grasp. And this is not something people did for a very long time. The hand would come in with a visual prediction, try to grasp. If it was unsuccessful, it would go back and revise its visual prediction and try again. So zero contact feedback. And so then imagine what you could do if you had even more. So I'm just very passionate about this space of how you sensorize soft hands. Okay, so that's all the background. Now I want to move into the first technology that we've been working on, which is a suction cup. Obviously not a beautiful humanoid multi-finger hand, but a technology that's really versatile. When I look at that Amazon pick and place scenario, suction cups are definitely going to have a role. And it's just very ubiquitous. So this is now an old clip from the Amazon bin picking challenge, where basically you're using visual predictors to find a spot to grasp and then try to grasp the object, and based on the outcome, update the performance. So is there a role for tactile sensing here? Do we need to keep grasping multiple times? Successful. And my background, how we got into this was my background in suction sensing. Okay, so this is a suction system. Can we use suction flow sensing for this? The next thing I want to just mention is that there's this perception that suction cups are just like, it's just a suction cup, throw it on there, it's good to go. This is a beautiful design space. If you look to buy a suction cup, you're going to find thousands and thousands of options that are specially tuned for all different circumstances. And there are engineers that dedicate their careers to this. I got to visit Festo, which was so cool. Pneumatics company has amazing robotic systems. And they were like, yeah, we design new suckers, whenever it's needed. And so this sort of specialization is very common. But as we're seeking grippers that can do more generic tasks in a flexible automation system, you maybe want one cup to be able to do multiple things. So that's one objective that we have. Okay, so after all of that, this is the Smart Suction Cup. Does anybody already know or has read about how it works? Oh, good. Okay. So what I want you to do is think very hard. Think about this. Oh, you can't see. Has that been in the way the whole time? Just now. Okay, good. So how do you think this works? There's no computer vision. We are monitoring the normal force and applying a consistent normal force, but the lateral motion is done through haptics, specifically through suction sensing. And this is on a bumpy surface that you would not normally apply a suction cup to, because maybe 20% of the surface is graspable with a suction cup. Any ideas on how this might be operating The tubes, all the tubes are the hint. Okay, definitely pressure sensing. Yes, pressure sensing is definitely involved. We're doing a flow estimate. And there are sort of these tubes going vertically. You can see 3 of them. Yes.
So is that like, if you have a constant flow, then you can use the individual independent tubes to understand what is the location?
Yes, exactly, exactly. So we got this idea, okay, you've got 3 independent tubes that are penetrating at different locations on the cup. What if one of them shows more flow than another? Then you get a bit of directionality as to where you're getting more suction. Exactly. So that's how it works. And I'll show you sort of the mechanical elements inside that allow it. So this was invented first by Tae-Mung Ha, who was a postdoc in my lab. He's now at UC Santa Cruz as a faculty member. And Monica Lee was an important part of this as our fluids expert. And the way it works is it has these 4 internal chambers. You can see that on the top right. So this kind of window shape. So the flow comes in and breaks up among all 4 of those chambers. It's actually all going to come back together. Let me get my pointer. It's all going to come back together about here. So it breaks up through this section and then it combines back together and then goes up and through this hose. So there's effectively no flow going through these hoses. Their only purpose is to translate the wall pressure here up to a pressure sensor here. So to move it away from the contact point to protect the more expensive electronics. Okay, and here's just another close-up of that geometry so you can see how they split. Then this is actually where they're going to combine back together and all the flow is going to go up. That's nice from an integration perspective with existing suction systems that have only one suction source. And this is cast in our lab. So we have a casting process. You basically pour the silicone in a 3-part mold and then you have to demold it. It's a little tricky right now, but we're working on improving that fabrication process. Yes?
I'm knowledge of demand, it's basically thing and then thing. Let's get these questions and they're not that long, but like they just
Delay. Yes, great question. So is there some sort of fluid dynamics or compressibility of the air in the tube that's going up? Short answer is yes, it is compressible. It will have dynamic effects. Likely what it's going to do is ultimately amplify quick events. So what we found, especially underwater, where things are even more sort of inertial, with the fluid is that it kind of, when you get a quick change in flow, it gave you a sort of a dynamic ringing, as this is kind of like a spring. So it's kind of like, whoa, you know. With air, we haven't seen it be pronounced, especially in comparison to noise. And we also, we tried to see how fast we could go, and we didn't really get to a limit on terms of how quickly we could do the sensing. So I would say it's yes, but negligible in the case that we see. Yeah. Great question. Okay. Of course, we do some fluid simulations because we're mechanical engineers. And this shows you sort of 2 opposite chambers as a cross section. And you can see that there is a difference in the pressure and the flow rate across 2 chambers that are opposite each other if the flow is going vertically here. So it would be like a via in your PCB and flow is going vertically. But we do need to be careful because same leakage side, but if the leakage is horizontal, like it's peeling off, you're actually going to get shoot through and the flow is going to go across and then up. So this is a convenient sensor and the logic could be simple, but it is important to understand that the physics is actually fairly complicated. And so the way you apply it might change based on the sorts of failures that you get.
Extend your partition.
Yeah, so this is a simplified model and we were trying to understand peeling, in which case you're pulling up and so the center chambers are pulling off. I mean, that could be a whole research project, is like, how do you maintain contact with the surface even with vertical displacement? But we were really focused on that pulling off case, not the pushing in case. When we're pushing in, all the walls are touching. Yeah. And then here's an example of what the signals might look like. The top is just a sum of all of them. So it's essentially, we're just taking an average. And you can see that when it's on the bumpy, when it's off the surface, you get no flow. maximum flow, which is no suction, then intermediate suction, and then maximum suction at the end when we go onto the smooth surface. The bottom was just an exploration of us looking at the left chambers versus the right chambers. And you see that there are these large spikes as we go past the off to on case. Okay. So that was our first set of experiments. And we also we did a bunch of experiments pulling it off of surfaces. And we collaborated with Professor Ken Goldberg's group to do some prediction. Can we predict when a seal break is about to happen and if it's going to happen on the left or right or front and back? And it turns out that, yeah, it seems like we can. We never took that quite as far. So that's basically where trying to prevent grasping failure after it's achieved ends. Moving forward, what we thought was really most interesting was, can you find a graspable location? And so we've shifted and now are focusing on that. And this is where Jung-Pyo Lee comes in, and he is now a postdoc in the lab, at the time was a PhD student, and started to implement different controllers using the logic of these 4 pressure transducers to come up with a way to find locations. The control logic that we just talked about, if left and right, if one is better suction, go that way, and then same with front and back, that's the logic that ultimately yields this very curious edge following behavior, which is so fun and interesting to see these sort of emergent behaviors from a seemingly very simple logic. And it ends up grasping it on a very bumpy spot. It's just good enough for it to actually grasp. So it's on top of an IC, an integrated circuit, and that's actually very common. Okay, so here's the controller, ta-da. We've got the west side, the east side, the north side, and the south side. For some reason, we rotate at 90 degrees. I don't know. I asked them why. They just said, we did it and it works. But essentially what you're doing is looking at north, south, and east, west, and trying to understand which direction you should go. And then you can do, so that would be sideways. But then there's also rotation. So if this side is not suctioned on as much as this side, we want to lower this side. So then you would do something like this. And we introduced this term alpha to be how much are we sliding and how much are we tilting. And so 0 would be 0 tilting. And alpha equals 1 means 0 sliding, only tilting. Okay, so we're just scaling them relative to each other. And then we tested them in, I think, 0.25 increments. Oh, and at this point, we have a lot of assistance from Sebastian Lee and Tae Mang Ha in doing the characterization and design of these controllers. And here's an example of us coupling it together. I do believe that this is 50-50, so half rotation and half sliding. And it is actually manipulating the object. We're just controlling normal force and then moving according to the control I just showed you. And it ultimately is able to find a good configuration for this loose object. Okay, so we wanted to test this against the state of the art of the time. So Ken Goldberg, again, his group allowed us to use their DexNet grasper predictor. And here's an example of a grasp that would have failed. So it's very close. You know, the visual predictor is very good, but it's not, it's like off by maybe like 5 millimeters. And if you were to just say, oh, it was unsuccessful, try again, versus actually saying, well, could we adjust just a little bit to make this a successful grasp? That's really the case that we're trying to create, okay? And so here, and we're not optimizing this for speed by any means. We're not computer scientists, but we do show that there is utility to this sense of touch. Okay. So our testing procedure to benchmark this starts using the GQCNN method. We have a depth camera here on the wrist. We look at that, we just use the algorithm as it is. We have not retrained it. It's a different robot arm, it's a different camera, it's a different set of objects, no retraining. So it's gonna make mistakes. That's essentially the point. And then it's going to go to where it thinks it should grasp. We then do feedback control on our haptic search controller. If it's successful within, I believe it's 10 seconds, we then move it. If it's unsuccessful in that 10 seconds, we call it a failure and attempt again. So how does this do? So the method non means just the visual predictor, no haptic search behavior whatsoever. no search behavior at all. So just goes, try to grasp. If it's successful or not, we call that a success or failure. This dashed line, so the number of picks is how many successful grasps that we've had. And attempts is the number of grasp attempts. So the dashed line would be 100% success until we run out of objects. So that's why it becomes a straight line. So you can see that as predicted, this visual predictor is not doing a great job because we didn't retrain it, and it's in a difficult circumstance. The best alpha that we found, which was some combination of rotation and translation, can improve performance quite a bit in this difficult scenario, although there is a large spread. And then just to be fair, we did a blind search. So just go in and randomly move around for 10 seconds to see if you can improve your grasp while maintaining your normal force. And that really doesn't help all too much. So the haptic information does have a role in this scenario. Okay. Is it fair that we are putting this visual planner method in a scenario where we know it might fail? I mean, I think you could argue that you should just retrain it every time. But in our sort of thinking in terms of like, how do you make a robust solution? I do think that this at the very least shows that tactile sensing could be one puzzle piece as we start to move to more flexible systems. And maybe this is a way that we can provide success while updating our models, right? So we know that our visual planner wasn't perfect. And then we know what configuration resulted in a success, right? So this could be really useful integrated solutions. Now we've been really interested in potential applications for this. So one idea was, where do you get objects that you can't have a perfect model for? Well, trash. Trash is always like different in shape, different in nature. And so in this case, we're trying to handle recycled PCBs. Okay, so recycled PCBs, all different shapes, might be bent or something weird. And we don't have a model for this. We're just basically segmenting the general shape and just saying, go to the center. So we want this to be fast and cheap and adaptable. So you can see that we are able to grasp the object after multiple attempts. There is, of course, integration challenges with this. When we first contact the object, it might move a little bit. And then our second grasp might be more random than it is actually haptically guided. So this is a first test and demonstration, and it's work that would need to be further explored. Yes?
Let me do some of the sorting. What's the benefit of grabbing compared to just like having flow into a box?
Flow into a box. Yeah. So if so I'm not like so we worked with somebody who's doing a startup on the recycling application. So I'm not the person who can best answer that question, but I do know that the vision is that you would have this full. Actually, do I have? I don't have the video, but in the UK, they have quite a couple companies that are doing this. And if you look at the conveyor belt, it's just like mounds of stuff, and there could be one little PCB in there. So if all the mounds of stuff just go into the dumpster, then it's just a dumpster. But if you wanted to pick out the PCBs from this other material, then you would have to do a more explicit like pick and place task. Did that answer your question? I see. So the sensor itself is giving you a reading of geometry as it relates to suction gripping. So it's actually our measure is closest to suction grip performance, not necessarily a direct measure of geometry, but those things are related. So you could potentially generate something like haptic maps of objects. So you just test like different objects that you might see, and you might see correlations between the flow readings and the different type of object. But I think probably if you wanted to do object recognition, you'd want to couple this with also a camera, and then maybe the information together would merge to give you the best predictor. Yeah, it's a good idea.
So have you guys tried yet? Discriminating between objects or?
We haven't. We're still just trying to grab stuff better. That's been really our primary focus. But we have talked about haptic visualization, basically like a haptic map of an object to augment a camera, right? Because a camera could tell that this is a smooth surface, but Could it tell that this is like semi-gloss or like how bumpy the stucco is? Well, a sucker probably could tell you how bumpy the surface is, right? So I think, this trade-off between vision, which tells you global things, and then the sucker, which tells you like details of like, there's a via here, like really small scale textures and friction properties, stuff like that. I think they actually complement each other really well. Okay. So that was the end of the suction cup. So any other questions on suckers? Yes.
Yeah, so it sounds like if you had a really cheap, small electronic pressure sensor, you could get rid of those pneumatic lines, right? What sort of do you need such a sensor, like the resolution?
So you're talking about like if you put pressure sensors on the lip itself?
Yeah, instead of having this like.
Yeah, so actually there's been quite a few, I would say it's kind of like fabrication material science side where if you have a soft element, you could embed conductive materials, or you could actually embed electronics directly into the rubber itself. I think that's what you're suggesting.
Yeah.
Okay, that has its advantages, certainly, but in the short-term translation, I'm a little skeptical. I think it's an interesting research area, especially from a materials and fabrication perspective. But what we found is that people who've done that, often it's ultimately just measuring sort of like pressure distributed. And if you don't have high enough resolution, you won't measure the geometries that we are actually sensitive to. Well, this sensor could measure very small cracks, right? It just says you have a crack that's impeding your suction grasp. We know that we've got an impeded grasp. And that is sensitive to very small features. We couldn't tell you exactly what that feature is, but we know it's there. If you have distributed pressure sensors, you may or may not be able to sense that. And it's a little bit, it's like one step away from the function of the gripper, which is to suck. So there's that. And then I'm actually going to get to this on the next slide. It's not scientifically exciting, and it's not something you would like to constrain designs, but people have this beautiful network of nerves, right? So how would you have a transducer in the lip of a soft cup and then have basically wiring that's going to be flexed again and again and again and again and again? And it has to go all the way through that cup and then up into your robot. Again, not academically interesting, but I think for translation, that's going to be a barrier for decades until we basically make nerve-like materials for robots.
What sense do they actually grab the thing out?
Well, so there's two.
Service line.
Yeah. Suck.
Grab this.
Yes.
Or I have to do it.
Yeah, so there's kind of there's two arguments. One is you're actually measuring the thing that you're closest to and not sort of trying to infer suctionability from geometry, you're just measuring suctionability. If you wanted to identify objects, then a pressure array might be better. Yeah, so that was back to the other question. But then the second thing that we've been really motivated by is, can we do a sense of touch without wires at all? Right, and that's really the benefit of having the air tube go up to a pressure transducer, and why we're not putting the pressure transducer down at the end where it would make it really bulky, expensive to replace. In this case, we can just pop off the passive rubber thing, put another one on. We don't have to recalibrate anything because we're just looking at differential pressures. Really just take it off, put another one on, and you can run your algorithm successfully. So that sort of insensitivity to variation and wiring is very powerful. So I do want to talk about distance of sensorization. So there are the solutions where you are integrating sensitive materials into soft rubbery elements. You could just embed a pressure sensor. Obviously, you can make them very small or really cool. But something like an FSR would be a very generic off-the-shelf option for that. And then you can embed them through like 3D printed processes and try to get the wires in there that way. If we take one step further, this is where we see a lot more translation in tactile sensors. Who's heard of GelSight or the camera-based tactile sensors? Really? Only 3 people? Oh my gosh, I thought this was like, everybody knows about this. So on the right-hand side, what you're essentially doing is saying, well, we don't want to have to deal with the wiring and the materials and it breaking. It's like $10,000 for one tactile sensor. Instead, we're just going to put a camera at the base, make the fingertip clear, and coat the surface with a reflective material so that we can visualize contact. So we can see the deformation. So this would be a geometry measurement. And then you could infer things like pressure and force, shear, and then ultimately, does that geometry support suction gripping? But again, it's multiple steps from the function. So it's very good for geometry. It has its own issues in terms of tactile sensing. Another option, though, to move that transducer, the electrical transducer, away from the contact is using acoustics. So, for example, I'm gonna do that. Pretend you didn't see me. What material am I stomping on? Something softish. It's probably carpet. So sound actually embeds a lot of information, and we can use that to our advantage. So you could have sound transmissions going through your soft structures that vibrate, and then therefore you can get contact information that way. Now we can go even further away, and this is where the flow sensing comes in play, where you're literally routing a mechanical coupling rather than an electrical coupling to measure the signal with some stiffness. Great question about fluids before. And people have done this in more closed systems where you have this 3D printed array with many pressure sensors. And then this one, the BioTac, uses actually the frequency and vibration. This is the tactile sensor that's set the bar in terms of function, but it is $10,000 per fingertip. So to get sort of the state of the art, there's typically a very steep cost curve when we're talking about a lot of sensation. Okay, so that was all sort of what I would call tactile sensing in the more traditional sense, where you've designed the sensor to give you specific information. But when we get the transducer really far away, what you're usually talking about is a microphone or a camera. So you could watch the scene, watch where the object is slipping, and infer something about the contact, or you could just listen to the coincidental sound like I just demonstrated to you. But what if I was on like memory foam? You wouldn't hear anything at all, right? So you're kind of at the whim of the environment. Is it well lighted? Does it have, sounds that are useful? So, what we wanted to do with this next technology that I'm going to introduce is to have that tactile sensor still, but to have it not be physically connected. So I would say that the smart suction cup was physically connected. And so now we want to take it sort of that next step. And again, we're going to use fluids to do this. One of my favorite sort of mechanical contact sensors would be something like a flute. Okay, so it is actuated. We do need to pump air into it and generate a unstable flow condition that makes it vibrate. But then if it's vibrating and we change our contact state, it will change its frequency. So if you record somebody playing flute, you could then decode what their fingers were doing because you know that mapping. Okay, so this is, I think, a really, really beautiful tactile sensor. This is ours. What it's all for. Okay, that's enough of that. So this is what we're calling acoustic. So acoustic tactile sensor. And so in this case, we are actually designing the sound that is emitted. We're not just getting coincidental sound. And then we can map the frequency that you hear to the force that you experience. And it sounds like a little choo-choo train because it has multiple frequency ranges. So there's 4 taxels, they're all at 4 different frequency ranges. And you will basically always get dissonance because we're continuously changing frequency by a little bit. And so you're never going to get a beautiful flute-like, chord, but you are going to be able to measure force. So our acoustic tactile sensor, it's no longer in preprint. It is also there, but it was recently published in Soft Robotics, which was great. And it has no electronics introduced at the contact itself. So it's something like this tin whistle. where you've got the fitball is the thing, it's basically a knife edge and the flow comes across it and goes unstable across it. And that's what's going to resonate the resonance chamber or the resonant tube. So this is what it looks like for us. It's a 3D printed section. The inlet comes in, it goes across this knife edge, it resonates this section, and then we've got a soft cap. Now, the frequency that's emitted should roughly be proportional to the inverse of that length term. So the length L of this section. And as we apply a force, this is going to compress and the length is going to reduce. So we're going to get an increase in our frequency. That's the prediction. There's different harmonics. It's related to how much flow you're providing. It's a little complicated, but you can, as long as you hold your flow consistent, it's pretty good. So we did some experimental testing with our robot arm, pressed it. We're just using a smartphone and a sort of analog flow meter. And this is what it looks like. So our amplitude of one signal, and then we're sort of pressing it 4 different times. And you can see that it's non-monotonic. Okay, that's interesting. But we are generally able to get these humps in the pressure reading or in the frequency reading. So let's zoom in on one of the 4. So here are the 4. Again, we've just changed the overall length for each one to get the different frequency ranges. And then we're going to press it with a certain amount of force. So you can see at first it goes up, then it goes down, then it goes up. This is not a very good sensor. If I'm reading a frequency of 1560, do I have 1 newton or do I have 4 newtons? I don't know. Okay, so this is generally undesirable. And you could just say, well, it's a good sensor over 5 newtons. In some cases, that might be fine. We were, of course, bothered by this. What's the physics? What's going on? And so the student hypothesized that you actually have this sort of weird boundary condition. And when it's not in contact and you just bring your finger down, you can actually feel it vibrating, kind of like a drum. And then when you press it enough, it stops vibrating. So you actually, that's just generating this nonlinearity at low forces. So we're designers. How can we get rid of that? Well, one idea is to add a hole. So what a hole does is it makes it so that you need more air to resonate. So that was actually the demo that you saw at first, where it didn't make a sound or not much sound until it was touched and then it resonated loudly. So you could then have an amplitude threshold. Another option is just to dampen out those vibrations by making the tip massive. So we just put some more mass on it. That also helps a lot. I'm just going to talk about the hole, I think. So yeah, here is the example of the frequency and the force, and then you get the amplitude. So without the hole, you get this sort of ambiguous, just constant-ish amplitude, but with the hole, you get this nice increase. So you could put a threshold at about 0.1 or 0.15 and get a nice transition. And then there you get your nice linear signal with force. Yeah.
So it's super cool work. Is the whole similarly inspired by the fluid design? Some of it.
That would be a question from Monica, who did this design work. She went down the rabbit hole reading all these like flow physics of musical instruments, and I'm sure at some point it percolated for her. But yeah, she ultimately introduced the whole. Yeah.
So if you look at the entire frequency spectrum instead of focus on just the peak.
Yeah.
With that extra
Here.
information.
This one? Or sorry, what are you looking at?
Because you're having trouble differentiating.
I see. So you're saying here, this plot?
Yeah, if you do the Fourier transform of the whole like signal, whole frequency spectrum, you'll be able to extract more frequency or more information to speak. Question.
Yeah. So like if you looked at a higher harmonic, would that give you different information that could let you differentiate? Yeah, so I remember Monica looking at different harmonic levels and trying to see if there was some sort of difference between the two states. It didn't immediately yield outcomes, so we kind of dropped that direction, but it doesn't mean it's not there. We just maybe didn't look hard enough. Certainly, I think there's probably, so again, we're not signal processing people. So we're kind of just using simple packages for design folks. And so ultimately these technologies need that sort of collaboration to take it to the next level. Okay. Of course, you can change the force sensitivity by changing the thickness, though the stiffness of the rubber cap. And you can also change the hole size. So when you make the hole very large, you can measure lighter forces, but then of course it's a little bit harder to seal it. So if you don't fully seal it, you won't get a signal. So these are all just general parameters of sort of tuning that you could tune for different applications. And then that's ultimately, we use a hole to get these very clear different signals at different points in the interaction. Okay, so I wanted to show one more example of this introduced into a system. So this is a soft finger. Now the entire resonant tube is going to be soft. So just the fipple is rigid, and then this is the whole resonant tube. And then you can also introduce holes and do sort of contact sensing here too. But here's just one example of what the signal could look like, where we've just correlated the sort of free curling behavior. So here we've got curvature and the frequency related to it. And it's very consistent, very linear from a sensor's perspective. It's pretty nice. Okay, and I'm going to skip this for the sake of time. So we get the question of like, well, what about background noise? You know, how sensitive is it to this? So I'll just play this video. So we're taking this with a smartphone, and you can see the signal getting a little weaker, but it's until we get near the shop, the machine shop, which has all its big fans and stuff, that we start to lose it. And even then, it's still kind of like it's able to kind of grasp it. So you can make this very, very loud, which has its advantages in non-human environments. But of course, this is very annoying and could even be dangerous. If you like accidentally pump too much air through, it could get very loud very fast. So Jade, who was the student who was most annoyed with this technology, decided to work on it and hopefully make it ultrasonic. So she's making them also smaller for higher resolution. We could do high resolution pressure sensing with this hopefully one day. Less flow needed. There's a lot of advantages to sort of reconfiguring what type of resonator geometry we use. So she's our next deep dive into fluids person. So just very high level, hopefully this has given you some new ideas about how sound or touch could be integrated into technologies that you are working on. I have this like fantasy that, you know, R2-D2 when he's like beeping and booping and has his own robot sound, maybe those signals actually have like foot force data in them, or like, you know, robot state could be embedded in like the human or the robot specific language. Maybe there is actually function layered in there. So just something to throw out in the world and see if it ever happens. But yeah, I think one thing just to keep in mind is that you know, what we're doing here with these graphs are actually very simple. We're just kind of gripping something or pressing something. So there's a lot of translation, and even with the sensors that we have, it's not the end of the story, right? It's one sensor in a suite. And when we have these really rich interactions with like PCB surfaces or weird geometries, there's an opportunity to get really rich information. Yeah, and just, you know, tactile sensors and hands, their entire purpose is to make contact with the world forcefully, repeatedly. So like people do hundreds of grasps in an hour. Could a robot really do that for a long time and not have sensors or wires fatigue? I think these are real questions for translation that are really relevant today. Hopefully material science and, you know, robotic nerves becomes a thing in a couple of decades. But I think for robots today, we need to think about a sense of touch without wires. And anecdotally, these are both very good. So they don't break, you can drop them, you can step on them, you can do whatever you want. As long as the electrical transducer is not getting stepped on, it's either easy to replace without calibration and easy to make. So I today gave you guys some insights into the tactile sensing area of work. I also gave you a brief intro on some of the older stuff that I did in underwater systems. I just want to point out that that's like half the lab. And so the other half is working on bio-inspired robots, a lot of rich contact with things like granular media or slippery surfaces. So really understanding that physics. And then also the really messy interaction of working with people who are super unpredictable, and it's always going to be an interesting research area. So yeah, that's the summary of the lab. And I do want to acknowledge the team of people who worked on this. Monica was a very big influence on this as my first fluids student. Jung Pyo did a lot of design work. And Tay down here and Sebastian also did a lot of work on the suction cup. All right, I'm happy to take any last questions or, yeah, see most of them.
I'm just curious how the suction cup behaves on like a porous substrate.
Yeah.
That you can really, that gives like a suction.
Yeah, so if it's so porous, so the question was about porous surfaces with the suction cup. If it's so porous, like very fine, like a brush, like the bristles of a brush, basically airflow is unimpeded by the material. The suction cup might not recognize that it's even sucking onto something, right? Because the flow doesn't change at all. So there's going to be a spectrum of objects that it can sense. If it's within its ability to sense a change in flow, then it will be able to say, I am on a non-graspable porous surface. So we haven't characterized that transition point, but that will be there. Yeah. But you could say if you have normal force readings that you're on a non-detectable object from the suction cup. But in the back.
I have a question about the smart section. So digital force numbers, it's sucker like
Yeah.
it's gripper. So what will it make any difference if we increase or decrease the number of channel like 3 and 4.5? So
Yeah.
will it make any difference?
Perfect question. That is what Genfio is doing right now. 1 is not enough, you get no directionality. 2, maybe you start to get, 1 dimension. 3, we're kind of seen as like a convenient minimum set, and it works. And the nice thing is that it's actually, the walls don't kind of jam up and buckle, so that it stays softer, which has advantages for grasping more objects. Okay, what about 5? What about 6? We've tested that too. And yes, it gives you a little bit more resolution, but if you change your behavior, what we're finding is that you might be able to emulate most of the resolution of a higher case. So let's say you rotate, or you do something that actually gives you more information to infer higher resolution, and then allows you to design and fabricate. So fabrication gets really hard beyond 4 in the process we're using. Yeah.
So use the 3D printed or just more plastic?
So the green one is cast. I think ultimately for adoption, you would want to do injection molding, but the internal geometry is pretty complicated. So having less cups would help with that. 3D printing, it's just kind of viscousy and ends up cracking after, 1,000, 10,000 uses. It's just not quite at the level you would want it to be. At least the ones we're using is not really long-term use. Yeah, but what our study uses 3D printed ones. Yeah. Yeah. In the back.
So obviously, potential child is smaller, it's all kind of smaller. Say having more chamber would cost.
Yeah. Interesting. I think you just touched upon like 3 different feces worth of work potentially, but it was like softer objects. Okay, so then you want to use less pressure, right? And so then your signal is going to be less, right? If there's flow. So yeah, there's going to be this complex design trade-off, as well as scaling. I mean, we haven't actually dealt with the scaling issue yet. The fluids will change when you get really small, or you get really big. There's a lot of really integrated design questions that you just asked about scaling it up across different applications. Really good questions, but I don't have the answers yet. Yeah.
I have a question about like the user of this work, and you mentioned a lot about haptics, tactile sensing. It seems like human hands are a big inspiration for it, so I'm curious if foresee like the ultimate goal to actually be able to replicate the sensing capabilities of.
It's a really good question. So it's about replicating human sense of touch. I think there's a lot we can learn from it. I'm not a proponent of replicating biology. You could take a crustacean and I'd be like, its tactile sensing is amazing. I'd be so blown away by its ability to respond to touch. So I think just generally, I'm amazed by sense of touch, but I am hesitant to assume that humans are somehow optimal or made of different materials. That itself might mean that there's going to be a different optimum for a robot. We also have historical evolutionary redundancies, like we've got 5 fingers. I would argue it's probably redundant. You could lose 1 or 2 and still survive the next day, right? Don't test it, but I think it's dangerous to assume too much about biology, but I do think that just consistently across like all of animals, you get a sense of touch. And there's something really powerful about that coevolution of this. Yeah.
Yeah, so, I mean, in terms of what I think this might from, as you mentioned, it's like from the platforms, I mean, in the microscope, there are also like textures that might lead to like frequencies, something like 250 hertz.
Okay.
Like for pneumatic, in pneumatic like tactile sensor, do you mention that pneumatic, such a tactile sensor may also detect like the vibrations or?
Yeah, so vibrations. I think vibrations are typically better transmitted through non-compressible fluids. So if you have a compressible fluid that's transmitting your information, it's likely going to dissipate quite a bit. But I mean, sound goes through air. So it probably just depends on amplitudes and the specific situation. Something to think deeper about. Like, good question. Yeah. Maybe just one more for the sake of time. We're at 5 minutes over now. Yeah.
You mentioned in the slides that our sense of touch has 2 factors. The one is we sense the force, and the other is when we move our hands, there will be. So, do you consider adding that kind of motion to instead?
Yeah, so it's very different, but we do call the haptic behavior where we're moving the suction cup haptic search. Right, so we're coupling behavior, or like if you spin the cup, you'll get more information about the surface. So we do call that haptic search. There's actually like lots of different ways that I meant it to be an example. We actually have 4 different kinds of mechanoreceptors in our hands. One is for skin stretch and all sorts of different things. And then we also have a number of different behaviors. So if you gave me an object and asked me how heavy it is, I would heft it, right? So I'm getting some information about the inertia of the object. So yeah, it's actually just a very generic term and was how I meant it to be. I think your question around texture actually comes back to the last question about frequency information transmitted through the air. Yeah, really good questions. All right. Well, thank you so much, everybody, for your questions.